Hello, my name is Richard Mandela once again. Um, Today I'm going to introduce you to the Spatstat package, a special package which was developed to analyze spatial point patterns. It's very relevant for ecology, forestry, and many other fields. You may have data for nesting birds, you may have data for tree species, you may have data for a different from different fields. For instance, if you have data for nesting birds or data for two species of crocodiles, you may want to look at whether these species may be territorial, or you may want to look at what patterns or what variables influence their distribution, what's their spatial structure, and many things. So Spatstat package is a strong package that is built around statistical principles. Uh, and today I'm going to take you through one of the principles and how it operates. But basically, we'll be looking at how to work around with Spatstat package with polygon shaped files as windows. And then I will talk a little bit about how to develop a point process model, which is designed around a Poisson distribution. So how it operates, you have point patterns at the side. These will be nesting birds, which are spatially distributed, and they're basically spatial coordinates from different areas or from your area of interest or study. There may be points for crocodiles. You may want to look at whether two species are territorial. You may want to look at the distribution pattern. You may want to look at the distribution structure, which you may test maybe to test a complete spatial or randomization process. But you may also want to look at whether maybe altitude, elevation, how it affects this species distribution, or you may want to look at the niches, how the niches are spaced apart for different species. So it's a strong package, as you can see, very important for ecologists. What you need to do is to have, when we are dealing with Spatstat package, when we import our points patterns, then we must give them a window. A window may be a rectangle, as you can see, or maybe a triangle, or maybe a polygon with irregular shape. When you import the points, when you import your points, then you put them into a window, which may be rectangular, as you can see here. But then you need the software, which is ARA, and then the package itself, which is called Spatstat. Basically, when you're dealing with it, you always have to install it from the repository. But you may not need ARA Studio. You may use just the ARA software. And then when you import this point may have what we call marks. That's the language. The marks may be if you have two species, then maybe if you have Crocodilus niloticus and then another crocodile species, Crocodilus niloticus may be marked as 1, and another species may be marked as 2. So when you talk about marks, we are looking at those corresponding attributes of the points pattern order you reference to points. And these may either be covariant, so I talked about the covariant briefly, but then the covariant may be an image, as you can see here, which is maybe like elevation, which may be like altitude, may be like rainfall patterns, maybe temperature distribution, maybe a lot of things. You may be slope, or maybe a function of XY coordinates itself, like a distance from the species, so it becomes a covariant, or it may be a distance. It is a very powerful package. And then the codes, which we are going to talk about here. the image, the covariant are normally stored as images, as you can see. You can see these patterns, which means that these varying RGB values, they have different values of a covariant. So basically that's it. Now we need to look at how to implement it in ARA. So I'm going to first of all show you that you need these packages. You need to first install this package, Spatstat. Go to the Spatstat library and load it. Mine is installed. So, and then one other important package is map tools, which we will use to load the polygon shape files, which we are going to use as windows, or others may be covariants. And then you can, I think those are the packages that we need for now. And then what we need is to give it a directory. And for now, I'll try to look at, I'll call a directory, whether I will see whether, so my directory is not well built. So I need to go to session and give a working directory where my files are. So my files here, I'll be basically working with that. So that's it. And now when I bring in, we run that code. I prefer writing. So when we say shape, we are going to import a polygon, which is going to act as a window for our point patterns. And what we do is we call it, we use this function, which shape spatial, into the name of the shape. This is the shape polygon that I want to bring in, okay? But then it has a file extension SHP, which is just an extension of an S3 shape file. Don't mind about the error, that's duplicated, it still works. So I'll show you what I've imported in here now. I'll show you what I've imported. Okay. We give it a little bit of time. I don't know, sorry. I think I have written a wrong one. Shape and SHP not found. Oh my God, what's the problem? We need to go back to our directory and say, I'll just rename this and just name this and then I don't know why. Need to find out. Yeah, I think the problem was the double quotes which were not properly specified. Yeah, so we can now run it. So that's the shape we have brought in. And now we need to convert. Spatstat package has what we call classes. It has a function called class which you can use to inspect an object. And if I'm going to inspect what I put in here, and then I will say class into shape, and then it tells you that this is an SP object. That means it is not recognized by Spatstat, but it's recognized by map2 package. So what we're going to do is to convert it to a window. So what we're going to do is to give it a name, and I want to call it object.window. And the function that we use is as dot a window into the name of the SP file. And now here you don't need to put the extension because R has already stored that object, and therefore it knows its extension by default. So it is already now converted. You may want to inspect it again and see whether it is successful. Now it is an O window. So a window means the window in Spatstat package. So that's basically it. So we can now bring in our points, and our points are named the export here. So if I run this code, it will bring the points. It is also duplicated. That's the error it brings, but it still works. If you don't want to receive this error, you can use the RGDL package. It also works well. So we can now plot these points. Remember that when I say plot, Spatial package uses OR uses plot.sp by default. But then even if I don't write it, it is still recognized here, so long as I put the right object into the parentheses. So I'll run it. And those are the points, but still I can inspect it for you. Class into point shp. It is still an SP, so we need also to convert it into a PP object. Now, Spatstat package recognizes point patterns as PP. It is a point process patterns. That's what it recognizes. So what it do is, I'm going to write that code now for that. And then I will name this x.pp because PP is the function, so it makes it easier for you to remember the assigned whatever name. So it will use as.pp, and then we put in the name of our shape file, which is now point dot shp. When we do that, and then we plot what we have just done, it's still the same. I'll use the default to give you I don't know why not find. Okay, sorry. Yeah. So when you plot it, it comes with all the what we talked about, the marks. And here the marks, you can see the point was recorded, and maybe some marks as they appear. But then we need to remove those marks. We don't need them now. That will be another tutorial. So I will use animark and into this pattern, the point pattern we have, and when I plot it again, it comes with a rectangular window. So, but we don't need this rectangular window. We need to give it a window as well. So let's give it a window. Let us give it a window. And just to make sure we can fall properly. Let's give it a window. To give it a window, remember the polygon that we brought in. We want to enter those points to this polygon to act as a window. If you remember very well my introduction, then you can follow properly. So what I'm going to do is this is a window, but I'm going to maintain the name. After all, I don't want it again. So then we bring this same point pattern now, and then we use those block brackets plus, and then we write object dot window. Remember, that was the name of the other thing. And so when we run, when I plot it again, uh, when I plot it again, you see the points have already gone in there. Okay, but then that's done. So what we need to do is, to bring in another point, because we want to write to generate a point process model, which I cite it is built around the Poisson distribution principles. Poisson distribution process, you know very well that it's where the variance is equal to the mean. That's the generalized linear model of family, which presumes that the variance is equal to the mean. If you want to read more, you can try Baddeley's paper, 2005. So I need to import the rivers. I want to look at how these points are distributed from the river, how the distance from the river influences the recording process of this species. So, but also, since this is a bivalve species that live in water and on land, also look at the distance from the ponds as well. And then we can also look at maybe the land use, or we can look at the precipitation patterns. So the principle is the same. These rivers are also in S3 shape files. So I'm going to run them. I already wrote the code here. So it's the same, but then the method for turning rivers into a recognizable object by Spatstat is a little bit different, and the code is as.psp. So what we're gonna do is look at the rivers. So what I'm gonna do is to run this code where we use as.psp, and then we write our polygon shape. Not a polygon shape now. It is line segments into a shape, a CHP file extension, which I've already written here, and we use the Spatstat option to check the segments. So checking the segment, it means we need to treat each segment as each segment has a single line, and then we use that as factor is true. When I run this, we can now plot the rivers. We can now plot the rivers. Plot into river. Actually, it was meant to be .psp. Let me change it to avoid confusing us. And run it again. So plot the rivers .psp. So those are the rivers. You can see each color is standing for different segment. Okay, so that's kind of the method we've used. And then you also need to look at need to correct my code here, because I may drop it in the link below. So now after plotting it, we need now to calculate the functional distance from the river, and we're gonna store this, and we store it will it will be stored as a little bit an image file with RGB values. So when I do this, when I run this, we use the distance function distfun to write. Yeah, that's the. Maybe I will just write distance river here to avoid wrong names. Distance river. So run it again. So when we're gonna plot, let's plot this now. Let's plot and look at this river. I named it this river, right? Correct. So it is now with different RGB values. You can see from the concentrated blue, it is a shorter distance from the river. You can see this from the river. As you move away from the river, the RGB value changes the colors. See? So, and therefore that means for away from the river, the distance increases. So what Spatstat does to model the spatial point pattern model is to look at how the intensity or the number of points from each distance, and then generates a model. So it's basically looking at counts. That's why it is based around the Poisson distribution model principles. So I can also bring in the rivers, and for time I will end on rivers. Then we shall run our model and there. So I mean the ponds. So the code for ponds is in here. I will just run and we just execute it. Don't mind about that. So because the ponds are like lakes, which are polygons with area. So they are not like continuous as the river. So we use the same function as I said. Then I will run that. So when we plot them, you will see them. So that you can see these points here, and then we can give it a window. We don't need to give it, but let's give it a window here. Remember our window, which is for the other polygon, is .ow object.ow. So we can run that. Maybe so that's the point. We can also get the distance from the point, and I'll write dist point. So I'll look at that. So change the name here. To save time, let me use the pre-written codes. So you say record that. And now we can also plot the distance points. Yeah, we can plot the distance points. And that's it. It's gonna come in a couple of minutes. Sometimes the delay. So you see the same principles. So we're gonna look at the distance, how the distance affected the recording process of these species that I've not mentioned here. So that is it. And now what we are left with is to build a model and then validate that model. What I'll first try to write the model one, and then say point process. The function is point process model, which is ppm. If you want help, you can just type in help into ppm or systematic search help into package equals Spatstat package. Then you get a lot of help from there. So remember our point pattern, which was stored as FPP, and now I can look at distance points first. But then it uses a formula now. So we look at, you see, the principles are the same. This is the formula we use for calculating linear models, the regression. That's means trend. So now we're gonna run it, but the data contains duplicates. So what we do, we're gonna remove the duplicates. Let's remove the duplicates. Remove duplicates. What I'm gonna do is give it an X, give it an X, and then I will say animal into X. So when we rerun our model, there is no that error. Oh, sorry, what's it? But anyway, the duplicates, don't really affect our. Let me look for the code here. They don't really affect. Say, they don't really affect duplicates. Anyway, they don't affect the model, but for now, I'm getting stuck with that. But this is just a demonstration, so so that is the model to give you a standard error and all that. If you may need to look at the area under curve for that model, which is model 1. You see, sorry, you see into M1. Oh yeah, that's the. So it's gonna give you a value which is 59. That means 59% of the distance. The river explain the shorter distance, because when you look at the coefficient here is negative 0.001. The shorter distance explains 59% of the recording of the species or the occurrence of the species. We're gonna now look at the ponds now. The river. Sorry, that was for the ponds. Now we're gonna look at for the rivers, and then we're gonna run an additive model. This is river, and sorry, I need to call this model 2. Need to call this model 2, and then I need to run. Yeah, it's 58. Yeah, that's 59. So let's see what happens if we combine the two covariants. So this points. Sorry, but anyway, let's run it. Let's run it. It's supposed to give it model 3, but that's okay. So the whole model is 6. When you combine the distance from the river and the distance from the pond, so you are able to infer whether the distance from the river affect the occurrence of the species or the pattern of the species in question. But you may also need to look at the receiver operating curves for the model, and I'm going to look at the model 3. And we use rock into model 3, which I refuse to change, and then we plot rock. We can plot rock now. You see, the envelope is that. You can look at the interpretation later. You need to validate these models. Let's first look at it by using the AIC. Let us first look at model 1. Model 1, it has an ICU 4377. What about Model 2? Model 2, sorry, how did I do that? I see. Oh yeah, one of it is not capital. It must be capital. So this is 434, and then it's 4377. The principle here is that the model with the highest IC is the strongest, and the model with the model with the lowest is the strongest, and then the model with the highest AIC is the weakest. So if you select the model, you can't go with only one variable. That means both the river and both the distance from the river and the points affected the recording pattern. But then you could also that could also be reflected in the area and the curve. Okay, so that is it. Yeah, that's it. And then there are other ways we can also plot the density of our point pattern. Sorry, density of our point pattern. Then plot the density. If you can see, this tries to predict where the highest recording is likely to occur. Basically that. A lot of things you may need to look at whether these points were clustered, dispersed, or you may want to look at okay, let's look at the quadrant, the goodness of fit for our model. Goodness of fit, which is also the quadrant dot test into we shall use our model 2, and then number of tensellations vary by 3. I'm going to show you that later. The counts are so small, but for the purpose of this video, I think to work for us. You can see what a quadrant is like. A quadrant, like you establish a quadrant plot, and then you count the number of species or the number of recordings in there. So what it does is to divide the polygon into equal units. These are equal units, so some of the shapes cannot be visually seen. And then it gives you the observed and the expected, the observed and the expected, and then the observed and the expected. So when we print this model also, you see the chi-square is, the p-value is very small, which simply means that these points are not homogeneous, like basically inhomogeneous. So they're not uniformly distributed. But then you can use replicate function, or you can use a G function text to look at whether they are distributed or not, by looking at the theoretical distribution and then the expected distribution. So that's it. Thank you for watching this video. Please subscribe to my YouTube channel. I will attach these scripts into the link below.